So in this video, we are going to discuss about DC performance characteristics of an opamp. So far we have discussed about an ideal operation amplifier which does no current from the signal source, right? And it is also independent of the temperature variation. But if you see the practical op-amp, it does varies by environment, that is by process parameters like temperatures. Okay, so the current is indeed taken from the source into the input of the op-amp. So it will the two input responds differently to the input voltage and the current. So okay, it is due to inherent mismatch among the transistors. Okay, so this is called as non-ideal. These are nothing but non-ideal DC characteristics because we are giving DC input and DC output. Okay, so non-ideal DC performance characteristics. So the first one is input bias current and input offset current. Next one is input offset voltage. Next one is thermal. So in this first let us discuss about input bias current. Okay, ideally if you see, we have this is nothing but an op-amp, right? This is minus plus and let me assume this is IB minus and this is IB plus. Okay, so what is IB minus and IB plus? IB minus is a DC bias current flowing into inverting terminal, inverting input. Okay, inverting input. And IB plus is DC bias current flowing into non-inverting input. Okay, so if you see inside this one, inside this op-amp, you have a differential amplifier, right? So inside this one, I have a differential amplifiers. Okay, so if it is an NPN transistor, means this IB plus and IB minus is flowing into this transistor. Okay, and if it is a PNP transistor, means it is going out of the current is flowing out of the transistor, right? So you can see this is nothing but a biasing current in order to turn on this transistor. Okay, but this value get varied. Okay, this two transistor must be identical. Okay, since it is a differential amplifier, this two transistor must be identical. So if there is any change in the value of the transistor, means that this IB minus and IB plus will change. Okay, so I can term input bias current is that is IB is equal to IB plus IB minus divided by 2. So it is defined as average of two input bias current. So IB, that is it's defined as, okay, average of two input bias current. Okay, let me assume this is how the circuit does. Okay. So this is nothing but an non-inverting amplifier, right? And let me term the current as IB minus, and this one as IB plus. Okay, current flowing through this one as IB plus. Okay, so you can see since this terminal is grounded, the IB plus will not flow into this transistor. Okay, so this value is this is nothing but so all the current will flow here. It will not flow through this transistor, but here you can see all the current will flow through this resistance. Okay, this is so this point is now it is, I can write this is V0, right? So I can write V0 is equal to, okay, that is 0 minus V0 is equal to IB minus right, IB minus into RF. Okay, so what is V0? V0 is equal to minus IB minus RF. Okay, so you can see instead of 0 voltage, I am getting V0 is equal to minus IB minus RF. Okay, so this has to be 0. Okay, so if I want to make it as 0, so I need to connect a compensation resistor at the non-inverting terminal. Okay, okay, this is a circuit I have installed. I have added one more circuit, that is our compensation resistor at the non-inverting terminal. Now this IB plus is it will not flow to the ground, right? Since I have added our compensation resistor. So here for this one, I am going to apply a superposition theorem. Okay, so for superposition theorem, you have to take only one current source at a time, right? So what I am going to do is I am going to take only this current IB minus at a time. So if I take the current as only one source, because since we are applying a superposition theorem, if I apply only one source, I will get the answer as 0 minus V0 is equal to IB minus RF, right? This is same as previous one. So V0 is equal to minus IB minus RF. Since there is no current flowing through this one, this point is 0, so this is also 0. Okay. So next I'm going to consider the second source, right? That is IB plus. Okay. So let me take this point as V plus. Okay. So what is the value of V plus? V plus is equal to V plus is equal to IB plus into RCOM. Okay. And I can write since V naught is since I am having a V plus here, I can write V naught is equal to V plus into 1 plus RF divided by R1. Since it is a non-inverting amplifier, I can write now I can write V naught is equal to IB plus RCOM into R1 plus RF divided by R1. And I am going to multiply RF on both sides. So if I multiply RF on both sides, I'll get, okay. So this is the answer. Since I have used superposition theorem, this is the second equation and this one is the first equation. So the total voltage I can write it as V naught is equal to, so let me term this one as V naught of A and this one is V naught of B. Okay. So this has to be V naught of A plus V naught of B. Okay. So the equation is minus IB minus RF plus IB plus RCOM RF into R1 plus RF divided by R1 RF. Okay. Suppose if I consider IB plus is equal to IB minus, okay, and RCOM value is equal to R1 RF by R1 plus RF. So what will happen? This is IB minus RF plus IB into R1 RF divided by R1 plus RF into R1 plus RF divided by R1 RF. So you can see this two term get cancelled out. So this becomes 0. Okay. So you can see I have eliminated the change in the output voltage. Okay. So usually you can see the IB value. IB value is nothing but 500 nanoampere. Okay. It is in the range of 500 nanoampere to it may go up to microampere. Okay. So if I use a precision opamp means this values will go as low as femto amplifier, femto amps. Okay. A means amps. So here in this equation, if I am not taking this IB plus is equal to IB minus, this if it is not same means I can rewrite this equation V naught is equal to that is IB plus is not equal to IB minus. Okay. So I can write this equation as minus IB minus RF plus IB plus RCOM RF into R1 RF divided by
Wait, go ahead.
R1 plus R1 plus RF divided by R1 RF, right? So we know that RCOM is equal to R1 RF divided by R1 plus RF. So if that is the case, I will get IB minus RF plus IB plus RF, because this to get cancelled out. So I can write RF into IB plus minus IB minus. This IB plus and IB minus is called as IB plus minus IB minus. This is called as input offset current. Okay, input offset current. Okay, so this is called as the definition is it is a difference between two bias current. It may be whether it may be greater, that is IB minus may be greater or IB plus may be greater. Okay, so this I can write it as RF V naught is equal to RF into IO. Okay, so it is defined as the difference in magnitude between IB plus and IB minus. So this if you see the IOS value, okay, so the manufacturer will specify the value of IOS when V naught is 0 and the temperature, okay, the temperature is equal to 25 degrees C, and the IOS value that is input offset value is equal to 200 nanoamps, okay, for BJT, that is if the input differential amplifier is made up of bipolar junction transistor, or it may be 10 picoampere for FET top-amp. Okay, so you can see the output voltages depend on the feedback resistance. Okay, so it can be either positive or negative DC voltage with respect to the ground. Okay, so I can term IOS value. So IOS value is less than input bias current. Okay,